Welcome to SciSpectrum Lab Essentials, your source for equipment, instrument, and consumables.
How do we actually measure something as fundamental as acidity or alkalinity? I mean, you can't see it. This isn't just a question for chemists in a lab. The answer has a direct impact on our health, our environment, and even the food we eat. For instance, think about a swimming pool. Keeping the pH right is this constant balancing act. If it gets too acidic or too alkaline, that perfect summer day can turn into skin irritation and cloudy water really fast.
And it's not just about us. It's also absolutely vital for delicate ecosystems. I mean, take the water in an aquarium. Fish need such specific conditions to thrive, and the right pH, that can literally be the difference between life and death for them.
And this idea extends to so many industries. The pH of a skin cream affects how it feels and works, and pharmaceuticals, getting the pH exactly right is critical for a drug's stability and effectiveness. It's everywhere.
Okay, so we've established it's important, super important. But what is pH really? Let's get into the science behind that simple little number.
Okay, so at its core, pH literally stands for power of hydrogen. It's all about measuring the concentration of hydrogen ions. But here's the part that's kind of mind-blowing. It's a logarithmic scale. That means every single whole number step is a 10-fold change. So a pH of 3 isn't just a little more acidic than a pH of 4. It's 10 times more acidic, and it's 100 times more acidic than a pH of 5. It is a seriously powerful scale.
And that's what gives us this familiar pH scale that you're seeing here. Anything below 7 is acidic, anything above 7 is alkaline, or what we sometimes call basic, and right there in the middle, smack dab at 7, that's neutral. Think of pure water, where everything is just perfectly balanced.
So, to measure all this, we need a special tool, and the real hero of our story today is the combination pH electrode. It's just a marvel of electrochemical engineering, seriously. So how on earth does it work? Well, it's this brilliant four-step process. First, the electrode's sensor bulb touches the liquid. That simple contact generates a tiny electrical voltage that changes depending on how many hydrogen ions are in there. So, the more acidic the sample, the higher the voltage. Then the meter's job is just to measure that tiny voltage and convert it into the final pH value we see on the screen. Simple, right? But to really understand how it generates that voltage, we need to look inside. So let's break down the anatomy of this really clever device. What you're really looking at is two electrodes cleverly packed into one. You've got a sensing part that actually detects the pH, and then you have a reference part that provides the stable, unchanging point of comparison. The meter just measures the voltage difference between those two parts, and voila, that's how it determines the pH. But here's where it gets really interesting. Not all electrodes are created equal. One size definitely does not fit all, and the design choices matter a lot, depending on what you're doing. First up, you have to choose the body material. If you're in a pristine lab working with some harsh chemicals or high heat, you're going to want a glass body. No question. But if you're taking measurements in a river or a busy classroom, well, a durable plastic body that won't shatter if you drop it is obviously the much smarter choice. Next up, the junction design. And this is critical. A single junction is totally fine for simple stuff, like tap water. But if you're measuring something with proteins, sulfides, or heavy metals, those things can actually react with the silver inside a single junction and just clog it right up. A double junction creates this protective barrier that prevents that kind of contamination. And finally, you've got this choice between sealed or refillable. A sealed gel-filled electrode is all about convenience. It's grab and go, zero maintenance. On the other hand, a refillable one, demands a bit more care, but it rewards you with much higher accuracy and a much longer lifespan. It's a classic trade-off. Okay, so let's see how all these design choices actually come together in a real-world example. We're going to look at a classic general-purpose electrode right here. When you look at the specs for this electrode, it's almost like it's telling you a story about what it's built for. The plastic shaft, that just screams durability. The sealed gel-filled reference, that tells us it's designed for convenience, not for someone who wants to do constant lab maintenance. And that single junction is the dead giveaway that this is meant for clean, simple water samples, not some complex biological gunk or industrial materials. So, you see how all these little design choices add up? They create this versatile workhorse that is perfectly suited for all those everyday jobs we talked about right at the beginning, checking the school aquarium, testing the pool, maybe taking some samples from a local stream. The design is just a perfect match for the task. And that's really the key takeaway here.
Behind every simple pH number, that one little digit that tells you if your pool is safe or your water is clean, there's this incredibly sophisticated piece of electrochemical engineering perfectly designed for its job.
It really makes you wonder, doesn't it? What other scientific marvels are just hiding in our everyday lives, just waiting for somebody to explain them? Thanks for joining us on The Explainer.